Hello everyone, I am Ajay Meddi, pursuing final year of Aeronautical Engineering at Institute of Aeronautical Engineering, Hyderabad. Yeah, in this video, I'm gonna talk about my tech talk concept called Experimental Assessment of Sound Quality Metrics for Takeoff and Landing Aircraft. Yeah, and this topic is from the Avionics and Control System subject. Yeah, and now we will discuss about the what is meant by the sound quality matrix for takeoff and landing aircraft. Yeah, the assessment of sound quality metrics for takeoff and landing aircraft is a paramount importance in understanding the subjective experience of aircraft noise and its impact on communities surrounding airports. While conventional noise metrics such as sound pressure levels provide valuable quantitative data, they often fail to capture the full spectrum of human perception and response to aircraft noise. Takeoff and landing phases represents critical stages of flight operations characterized by high noise levels and significant community annoyance. Therefore, evaluating sound quality metrics, especially during these phases, is essential for accurately accessing the overall noise impact and informing effective noise mitigation strategies. This presentation focuses on the experimental assessment of sound quality metrics tailored to the takeoff and landing phases of aircraft operations. By systematically evaluating various metrics against subjective human responses, this research aims to provide insights into the effectiveness of sound quality metrics in capturing pre-received noise quality during this critical operational stage. The findings of this study hold significant implications for aviation stakeholders, including airport authorities, regulatory bodies, aircraft manufacturers, and affected communities by informing the development of noise abatement measures and fostering sustainable aviation practices. Overview of existing sound quality metrics for aircraft noise. Various sound quality metrics have been developed to assess the subjective experience of aircraft noise and its impact on communities. These metrics go beyond traditional measures of noise intensity such as sound pressure levels by considering additional factors that influence human perception and annoyance. Some of the key sound quality metrics used in the evaluation of aircraft noise include tonal content. Tonal components in aircraft noise such as engine winds or fan tones can particularly bothersome to individuals and contribute significantly to overall annoyance. Metrics such as tone to noise ratio, tone corrected sound pressure level, and tone corrected perceived noise level quantify the prominence of tonal components in aircraft noise and their contribution to perceived annoyance. Fluctuation strength. Fluctuations in noise level over time, commonly referred to as amplitude modulation, can significantly influence the perceived annoyance of aircraft noise. Metrics such as modulation depth and fluctuation strength quantify the degree of amplitude modulation in noise signals and its impact on perceived annoyance. Impulse content. Impulsive events in aircraft noise such as engine transients or thrust reverser operations can be particularly disturbing to individuals, especially during critical phases of flight such as takeoff and landing. Metrics such as impulsiveness factor and impulsive noise level accesses the impulsive of noise events and their contributions to perceived annoyance. Low frequency content. Low frequency components in aircraft noise, often generated by large aircraft engines or airframe aerodynamics, can penetrate buildings and cause structural vibrations, leading to increased annoyance among residents. Metrics such as low frequency content and low frequency corrected metrics quantify the level of low frequency noise and its impact on indoor and outdoor environment. Experimental setup description: an anechoic chamber or outdoor testing area was utilized to minimize external noise interference during experiments. The aircraft noise was simulated using recorded sound samples or generated by model aircraft engines. Microphones were strategically placed at predetermined locations to capture noise level accurately. The experimental setup ensured control conditions for consistent data collection and analysis. Instruments used for data collection: sound level meters or noise dosimeters were employed to measure sound pressure levels (SPL) at various frequencies. Spectrum analyzers provided detailed frequency analysis of the recorded noise signals. High quality microphones with calibrated sensitive were used to capture sound data with precision. Data acquisition systems facilitated real time data logging and analysis during experiments. Parameters measured during experiments: sound pressure levels recorded at different frequencies to access the overall noise intensity. Frequency spectrum analyzed to identify tonal components, modulation, and low frequency content. Psychotic parameters: loudness, sharpness, and roughness were quantified to evaluate subjective noise perception. Impulsive characteristics, impulsive content, and impulsiveness factors were measured to access transient noise events. Environmental conditions, temperature, humidity, and wind speed were monitored to account for their influence on noise propagation and perception. Conclusion: the experimental assessment of sound quality metrics for takeoff and landing has provided valuable insights into how aircraft noise impacts communities. By evaluating various metrics, including tonal content, fluctuation strength, and psychotic parameters, the study sheds light on subjective experience of aircraft noise during critical flight phases. The findings underscore the importance of considering multiple metrics for a comprehensive understanding of aircraft noise. These insights can inform targeted noise mitigations strategies and the development of quieter aircraft and flight procedures.